The last topic in this unit is about entropy balance, just like we did energy balance, except that entropy is not a quantity that is conserved. Entropy is not a quantity that is conserved. What do I mean by that? If you start with x joules of energy, at the end of the process, you will still have the same x joules of energy, although the form might have changed from heat to work or work to heat, internal energy to work, and so on. Okay. Entropy, on the other hand, is not a quantity that is conserved. We saw that the entropy generation term is always 0 or more than 0 for any process that takes place. Okay. So if we write a balance like saying total entropy entering a system minus total entropy leaving the system plus entropy generated this is the change in entropy of the system. That is S inlet minus S exit or outlet plus entropy generated is equal to delta S for the system. This is for a closed system. Okay, this is for a closed system. Now, if we think of open system, we can think of the entropy related to heat transfer. The entropy related to heat transfer is Q divided by T, where T is constant and Q is the heat transfer, that is internal and reversible. Okay. Entropy transfer by work is 0. Entropy is not something you can transfer by work. It is simply equal to 0. The entropy transfer with mass flow, S mass, is the mass flow multiplied by the entropy per unit mass. Mass flow times specific entropy. Okay. So if we have a mass flow rate, the rate of change of entropy transfer per second is mass flow rate times the entropy per unit mass. And then we have entropy generation. S gen, which is usually related to friction, mixing, chemical reactions, other types of irreversible processes. Okay, so if we put all this together in a rate form or for an open system, S in dot minus S out dot plus S gen dot equals ds system divided by dt. This is the rate of entropy transfer by heat transfer. Okay, this is the rate of entropy generation and this is the rate at which entropy changes for the entire system, rate of change of entropy. Okay. For a closed system, we'll simply write summation of Qk divided by Tk plus Sgen equals delta S system, which is S2 minus S1. By closed system, we mean a system across which you can transfer heat or you can transfer work but no mass. Okay, Qk and Tk are the heat transferred. There can be multiple ports through which you can transfer heat, and the temperature at which those heat transfers are taking place. So like for example, this could be K equals 1, this could be K equals 2, this could be K equals 3. At one point you may be heating or transferring heat, at one point you may be cooling or removing heat, and so on. Okay. So some special cases, if you have an adiabatic process, Q is 0, which implies Sgen, the entropy generation, equals change in entropy of that adiabatic system. You could still have entropy generation in an adiabatic process. There could be mixing or friction. Okay, it's only adiabatic and not isentropic. Okay. For an open flow system or a control volume, open flow systems or control volume, let's say we have an inlet and an outlet or multiple outlets and multiple inlets and so on. So in this case, Qk dot divided by Tk plus m dot Si inlet flow times the entropy at the inlet state minus outlet flow times the entropy at the outlet state plus Sgen equals S2 minus S1 for the control volume. So this being your control volume. The entropy change for the control volume is due to heat transfer, entropy of incoming fluid, entropy of the fluid that's leaving the system, plus the entropy generation within the system divided by dt. Okay. So if we think of a steady flow system that we only deal with in this class, we'll write d over dt S2 minus S1 is 0, or the entropy generated is equal to sum of me dot Se minus mi dot Si minus Qk divided by Tk. Okay. Qk, remember, is the heat transfer rate. And Tk is the temperature at which heat transfer takes place. Temperature. So for a steady flow process, entropy generation is equal to the exit minus inlet minus the heat transfer divided by temperature. Okay. So if you have an adiabatic process, or if you have a process in which there is flow but not heat transfer, Sgen equals me dot Se minus mi dot Si. Okay, this would be the entropy generation in me dot Si. Recall when we did energy balance for a steady flow system, you would have the energy coming in and the energy leaving out. Okay. For entropy, this is the entropy generation. This is not a balance. What comes in doesn't equal to what leaves. For entropy, there is always generation, and this generation is equal to the difference between what goes out minus what came in. Okay. So as far as problem solving goes, I'll state two key important for open flow systems. Okay. Sgen, rate of entropy generation, is me dot times Se minus mi dot Si minus summation Qk dot Tk is the equation that we'll use for problems. For closed flow systems or systems with no flow but only heat transfer, entropy generation plus summation Qk Tk equals S2 minus S1. Okay. So these are the two main equations that you should know for solving problems in this unit. So with this, we wrap up chapter 7 or the second part of module 6, where we saw what is entropy, we saw what is the Clausius statement, okay, we saw the quantitative generation or quantitative definition of entropy, with entropy generation being more than or equal to 0, which is what we call as the second law, which is what we call as the increase of entropy principle. Okay, and then we saw how to calculate entropy changes for liquids, solids, and then gases, ideal gases. We saw what is isentropic, and then we saw what is isentropic efficiency, and then we saw finally entropy balance for closed and open systems. So this is all covered in chapter 7.1. We started with 7.6, 7, 1, 2, 3, 4, 5, 7, 8, 9, 12, and 13. We'll see these through problems during lecture time. Thank you for watching.